Welcome to online training session day 5, in which I am going to cover the different analysis which we can perform using radios as a solver and creating the deck for it using HyperMesh, and after that viewing the results in HyperView. As there are many more analyses which we can perform in HyperWorks tools, so that's why I divided this session into two parts. That is part 1 and part 2. So today I am going to cover somewhere around 10 tutorials on different analysis, and in the next part I am going to cover the rest of the 11 tutorials. So this is our training series details, in which we have covered till date. We have done with day 1 training session, day 2, day 3, day 4, and so we are on to day 5, that is analysis and post processing. So the topics which I am going to cover for this training series is linear static analysis of plate with hole, thermal stress analysis of coffee pot lid, then normal modes analysis of splash shield, 3D inertia relief analysis using radios, 3D buckling analysis using radios, connection of dissimilar meshes using C-weld elements, analysis of composite aircraft structure using pre-com G card image, that is a card, then analysis of axisymmetric structures using radios, coupled linear heat transfer / structure analysis, and lastly we will see setting up model analysis. So we will start our session with linear static analysis of plate with hole. This tutorial demonstrates how to create finite element on a given CAD geometry of a plate with a hole, apply boundary conditions and perform a finite element analysis of the problem. Post-processing tools will be used in HyperView to determine deformation and stress characteristics of loaded plate. The exercise includes setting up the problem in HyperMesh, applying loads and boundary condition, submitting jobs, and lastly we will see how to view the results. So we will start with opening of HyperWorks. Select the user profile as radios bulk data, because we are going to use radios as a solver for different analysis. So we will select radios bulk data. We will click on open folder. It's loading, so we'll click on open folder, browse the location, so this is the plate in which already 2D mesh is done. So it has the component. If I change the color, you can see. So in this, on this plate, the 2D meshing, that is elements are already present. There is no geometry. So these are only elements, as you can see. So we'll start with the process which I have explained earlier also, that is first step is to create material. So we will first create the material using material collector icon. So we'll click on this. Enter the material name as steel, define a color, select the type as isotropic and card image as matte 1. Then I will click on create edit to input the material properties like E, new, rho, that is Young's modulus, Poisson's ratio, and density. So I will enter E, new, and rho. Then I'll click on return. Again I will click on return to exit the material collector icon. So you can see on the model browser my material is created. Now the next step is to create the property and update the component later on. So to create the property, we will click on property collector icon on just the right side of material collector icon. We will enter the property name as plate hole, define a different color so that I can see on my elements whether the property and material are assigned or not. Select the type as 2D because this is 2D elements. So we will select the type as 2D and card image as P shell because they are shell elements. We'll click on material and select the material which we have created earlier step in material collector. Then we will click on create edit, and here we will input the value of thickness. So I'll assume the thickness of the plate to be 10 mm. All these tutorials is to understand you how to create a solver deck for the different analysis. So they are just the examples to understand how to create a solver deck in HyperMesh for radios. So if you want to perform any particular analysis, what are the steps you have to follow? So the values which I will take are all generalized value. So as per your requirement, you can change these values. So once I will input the value of thickness, then I will click on return. Again I will click on return to exit the property collector panel. So on the module browser you can see my property is also got created. Now the next step is to create component. But as you can see here, the component is already created. So we will update this component with proper property. So to update the component, click on components collector icon on the left hand side of material collector icon. Here instead of create, we will click on update radio button to update the component, the existing component. Then we will click on comps on the yellow box, select plate hole component which is already created. From the no property, I will toggle it to property and I will click on property and select the property which I have created. So once I select the property, you can see my card image will get automatically selected as P shell. That means it captures the thickness. My material steel has been assigned with the material card image, that is MAT1, so that my elements will get assigned the material properties of E, nu and rho. Then I will click on update. Once I click on update, we can check whether the property and material are assigned or not by changing the thickness to 3D element representation. So now you can see they are properties assigned to it of thickness 10 mm, and by element color mode I will change this to by property. So all the elements color will get changed as per the color of property. Then by material, so my color is changing by material. So always it is advisable to check it whether the elements are assigned with proper material or property or not. So these are the two checks through which you can confirm that whether it is proper property and material is assigned or not. So once this is done, then click on return to exit the component collector. Now the next step is to apply loads and boundary condition to the model. For this particular example, I am going to constrain the two edges for all the degrees of freedom and apply a total load of 1000 Newton at the circumference of the hole in positive Z direction. So if I put it in XY plane, so you can see out of this plane I am going to apply the force. something like this in this direction. So to create the forces and constraint, first I need to create the load collectors, the respective load collectors. So we will start creating that. So to create the load collector, first I will click on load collector icon. Enter the load collector name as SPC. SPC stands for single point constraint. Define a color, so it will be easily viewable in the GUI itself that the constraints are, these are the constraints. So I will click on create. So on the model browser you can see my load collector as SPC is created. Then I will change and create one more load collector as force, putting a different color on it, and again click on create. Then once my load collectors get created, then I will click on return to exit the load collector panel. So now you can see my two load collectors SPC and forces are created on the model browser. So now I will apply the constraint on the model and forces. So first of all we will apply the constraint on this. So always make sure the SPC is your current one, but as you can see the force is bold, so that means it is the current. So right click on it and click on make current. Once you click on make current, the load collector SPC is the current, so whatever the constraint you will apply, it will directly move to the SPC load collector. So to apply the constraint on your model, go to analysis page. On analysis page, click on constraint. We are going to apply the constraint on these two edges. So shift plus left mouse button and drag a window to select these nodes. So I am going to apply the constraint on these two edges with all the degrees of freedom, that is translation along XYZ and rotation about XYZ fixed, and then click on create. So as the size is very small, so you can increase the size so that it will be easily visible. So you can see my constraints are now created. If I on this, so you can see it is showing that this point is constrained for 1, 2, 3, 4, 5, 6 degrees of freedom. If I off this, so this will be off. Now the next step is to create or apply the forces. So I will right click on the force, click on make current. I will click return to exit the constraint panel, and on analysis page I will click on forces, and I will change the selection mode. So press shift and double click on anywhere on the GUI and select a different mode of the selection. So instead of square you can have circular, so it will be easy for us to pick those nodes around the circle. The direction of force which I am going to apply is Z-axis. Then I will again show you, I will pick this and if I off deselect this, so there are 47 nodes on the circumference of this circle. So I am going to apply a total force of 1000 divided by 47. That means on each node I am going to apply a force of 21.27 Newton. And click on create. So once I click on create, still the magnitude is very small, so I will increase the magnitude. And on the load collector, so you can see this force are represented by arrows. So you can see on the z-axis, on positive z-axis, it is showing that the forces are applied, and the magnitude of force it is showing as 2.1 e to the power 1, that is 21.277. Now, after defining the applying the forces, the next step is to create the load step. So we'll click on analysis and define the load step. So analysis, load step. In load step, we create the load step to define the type of analysis which I want to proceed through radios. So through radios, you can go to these many different types of analysis. But by which type of analysis you want to perform on your model, that you have to select. So that's why we need to define the load step. So as I want to perform linear static analysis, so I will select the type as linear static, enter the name as say plate with hole, check the box in front of SPC and load, click on is equal to symbol and select SPC load collector, click on load and select force load collector. Once you select it, it will show you the numbers as 1 and 2. These numbers are the load collector numbers. So SPC contains number 1, forces contains number 2. So it will always show you the numbers. So cross check it whether the load collector assigned numbers are correct or not. Then click on create. So once you click on create, you can see on the model browser that the load collector, sorry, the load step is being defined. So I will click return. Now I will save this file and using radios as a solver I will solve it. So to submit the job for the solver, on the solver, we'll click on analysis, radios, select the export option to all, run option to analysis, memory option to default, click on radios. Once you click on radios, it will start the solver window, and at the end of the analysis it will show you that analysis completed. So once this message comes, close the solver window, go to the visualization options at the top, split this window into two, that is on the page window layout panel, select the drop box, divide the screen into two and click on the second screen. Once you click on the second screen, it will redirect us to HyperView GUI. So this is the HyperView GUI in which we will load the result file. So I will go to So these are the files which it has created. So different file contains different information. So to view the results, we will click on or we will open H3D file or HyperView player file. So I will select plate with hole.h3d. You can see here on the file type, that is, this is the H3D file which contains the result. I will select this and click on apply. So once you click on apply, you can change this two window into one by expanding it. So on the complete GUI you can view the results. To view the deformation or displacement or stress values, click on contour. Select the result type as displacement and click apply. So the maximum displacement, if I click on the measure, static minimum maximum, so my maximum displacement is coming as 0.274, and if I want to go to elemental stresses, one my says averaging method to simple and say apply. So my maximum stress is coming as 7.1. So in this way, these are the results of displacement and stresses. You can also view the animation, how this plate is going to behave if this type of loading condition is there. That is also possible in HyperView. So click on this animation, but as the deformation is very less, you can see if I change this, so as you can see the deformation is very less. So we have to increase the deformation value so that the visualization is quite easily viewed. So we'll click on deform icon and increase the scale factor. And if I on the wireframe, so you can see, I will lower down the speed. So if I pause this and make it to the end, you can see I will change the color so it will be more visible. So now you can see this. Also I will off this. So earlier the position of plate is this. So due to the application of force and application of constraint on this location, the plate is going to move something like this, which is practically same which I am thinking. So this is the animation plot. So you can view this. Now we'll move to the next tutorial. In this way I have ended with this tutorial, so I will move to the next tutorial. So I will go to this, I will pause it, click on the new, again I will click on new and make it in the single window. So now I will move to the next tutorial, in which I will show thermal stress analysis of coffee pot lid. In this tutorial, an existing finite element model of a plastic coffee pot lid will be used to demonstrate how to apply constraint and perform radius finite element analysis. HyperView post-processing tools are used to determine deformation and stress characteristics of the lid. In this exercise, we are going to perform the retrieve. We are going to see how to retrieve the HyperMesh database file, set up the problem definition in HyperMesh, apply the loads and boundary condition to the model, submit the job on radius, view the results using HyperView. So again, I will open HyperWorks Student Edition version 11. Click on Model View. Open the file coffee_lid.hl. So in this, you can see the loading condition, that is the thermal loading conditions, are already defined. But the material is not created. So you can see my component is created, my property is there, but there is no material. If I off this, so you can see. So first of all, I need to create the material. I will enter the material name as plastic. Define a color. Select the type as isotropic. card image as mat1 and click on create edit and enter the values of in new row for the plastic. So for plastic, I will enter the value of E as 1137, new as 0.26, and instead of row I will select A as 81 e to the power minus 6. Then I will click on return. So in this way I have created material as plastic. Now I will create or I will edit the property which I have already created. You can see here the property is already created, so we will just edit or update the property with proper material. So I will click on property collector icon and go to update, select the property which I want to update. So I will select P shell. On material I will select plastic, so I will select type as 2D, card image as P shell, material as plastic, and click on create edit, update edit, and verify that the value of thickness is given as 2.5 or not. Then again I will click return. Again I will go to property collector icon, click on the property and update P shell.1, type as 2D, card image P shell, material as plastic. Click on update edit and verify the thickness is 2.5 or no. Now we will create and we will apply the loads and boundary condition. Before that we will cross check with the components 2 that P shell is updated with the proper materials or not, and this one is not. Yeah, both the components are properly updated with the properties. Now we'll apply the loads and boundary condition on the model. So the thermal loading has already been applied on this model. So in this we'll apply the constraint on this model. So for that we will apply the load collector as constraint for as SPC. Define a color and say create. So I will apply the constraint. So analysis constraint. So first I will apply the constraint on these two edges for the degree of freedom 3. Then instead of constant value, or first I will create a node for applying the next constraint as 0, -10, 0 and say create. So this is one node I have created to apply the constraint on equal distance on the both the sides. So now we will constraint I make it like this, so now we will constrain these two and these two for translational degrees of freedom. And then click on return. So I have applied the constraints and thermal loading. Then I will press Shift F2 to clear this node. Yes. So now I will create the load step. So analysis, load step, through which I will define the type of analysis which I am going to perform. So I will again select the type as linear static, enter the name as view cycle, check the box in front of SPC and select the SPC, and check the box in front of temperature and select thermal loading, and then click on create. So my load step has been created, as you can see here. Now I will run this analysis or submit the job in Radios. So before that we will save this file. So file, save as model, create a new folder as thermal analysis. Go to analysis, Radios, export option to all, run option to analysis, memory option to default, and then click on Radios. So my analysis completed results is showing. So I will close this solver window. Okay. So I will split it into two windows and click on the second GUI to open HyperWorks player. Click on folder option and select the file, the H3D file. Click on expand reduce window. Go to contour and select the displacement. You can click on static min max. So this is the minimum displacement due to that thermal loading. And these are the stress values. So this is the animation plot. I can increase the deformation too, so you can see this. If I make it in a wireframe, expanding it, so you can see. This is thermal expansion. I'll lower down the speed. So in this way, we have ended with this tutorial. Now we will move towards the next tutorial, that is normal modes analysis of splash shield. In this tutorial, an existing finite element model of an automotive splash shield will be used to demonstrate how to set up and perform a normal mode analysis. HyperMesh post-processing tools are used to determine the mode shapes of the model. The following exercise includes retrieving the Radios input file, setting up model in HyperMesh, applying loads and boundary condition to the model, submitting the job and viewing the results. So we'll again open the hypermesh, click on new, again click on new. So for this tutorial, I will import the solver deck, that is FEM file. So I will click on import. Select the import option all and keep all the other parameters as it is and click on import, then click on close. Go to model browser. So if it's in a line mode, you can click on this icon to convert it into shaded geometry. So first of all, we will review the rigits. So there are two rigits locations. Here you can see if I click on this. So there are two bolting locations of it. Then we will start with again setting up the material and geometric properties. So my material is already created, property is already there, component is already there. So I have to edit those. So I will right click on it and click on card edit. So here you can see the values are already entered as 2.0 e to the power 5, 0.3 and 7.9 e to the power 9. So everything is perfect here. I will click return. So I am just checking whether all the material and properties are properly defined or not. Then for the property, so MID, that is material ID 1, is defined. Then we will change this thickness instead of 0.3 to 0.25. I am changing it because I want to show you that how we can change the thickness values. And again I will go to property. There is a another way. Select the non-design one, 2D, P-shell, GN, update edit, and changing the thickness property from 0.2 to 0.25, 0.3 to 0.25. Then applying the loads and boundary condition on the model. So for the model analysis, we create EIGRL card image where we define the initial and maximum frequency range, or the maximum frequency or number of modes. So first of all, we will create the load collector with the load collector icon as EIGRL. Enter the card image as EIGRL, defining a color, and click on create edit. Enter the value of V2 as 200 Hz and ND stands for, I'll put ND as 6 for the first 6 mode shapes. Keeping all the other parameters as it is, I will click on return. Now I will create one more load collector as constraints without any card image and say create edit. So on the model browser you can see if I change this color, my constraint as a load collector has been defined. Now I will apply the constraint on the model, so I will go to analysis constraint. And I am going to constrain these two bold locations for all the 6 degrees of freedom. I will increase the size. So if I off this, so that you can see the constraints I have applied. Now we will solve this model, but before that we have to define the type of analysis. So we'll create the load step. So we'll go to analysis, load step, select the type of the load step as normal modes, enter the name as bolted, check the box in front of SPC and provide constraint, and check the box in front of method structure and input the value of EIGRL and click on create. So on the model browser you can see my load step has got created. Now I will save this file and solve it using radios. So analysis, radios, export option to all, run option to analysis, memory option to default, and click on radios. This will start my solver, and I got the analysis complete message, so I will split this into two. Click on the open to browse this file. Open the H3D one and say apply. As you can see, the deformation is very high, so I will decrease the deformation value. And we will see different modes. So this is the first mode, this one is the second, this one is third. Also I will check the measures. Fourth, fifth, sixth, and then first. So there are 6 modes, 6 different modes. So in this way, if you want to perform the modal analysis on your model, so you have to define EIGRL card and appropriate constraints to perform modal analysis on your model. So now I will pause this, click on new, this is also new, and split it into single part component. So now we'll start with the next tutorial, that is 3D inertia relief analysis using radios. In this, an existing finite element model will be used in this tutorial to demonstrate how HyperMesh may be used to set up an inertia relief analysis. The analysis is then performed using radios and post-processed in HyperView. So the following exercise include setting up the problem in HyperMesh, submitting the job, and viewing the results. So I will click on open folder and open the 3D inertia file. Now I will start with creating the load collectors which we can use to conduct the inertia relief analysis. So we'll click on load collector icon. Define the load collector name as static loads. Define a color. Define the no card image and click on create. And we'll create one more load collector as SPCs. Define a proper color with a no card image. Again click on create. So I have defined two load collectors, that is static load and SPCs. Then I will create the support one for analysis. So I will go to analysis, constraint, and select the load type as support 1 for 3D inertia relief. Then for these two locations, for this and these two nodes, and we will select these 2 degrees, deselect these 2 degrees of freedom and click on create. So my 2 load collectors has been created. Or I will deselect this and say create. And for the second one, I will deselect the degree of freedom 1 and say create. So if I off this, so you can see I have applied 2 constraints. That is, one is 1, 2, 3, 5 and second is 2, 3, 4, 5, 6. Now for the another constraint, I will select this node and deselect the DOF2 and say create. Now we will apply the static forces. So I will make this static loads as make current. Go to analysis, forces. Select the node where I want to apply the forces. Select the magnitude as -1 e to the power 5 and in x-axis and click on create. Then we'll select the same node, select z-axis and apply at 3 e to the power 5 and click on create. So these are the 2 forces which I will apply. Then we will define the load step as analysis load step. Enter the load step name as linear. Select the type as linear static. Check the box in front of support 1 and select SPC. And check the box in front of load and select static load. And click on create. For the inertia relief analysis, we have to define a control card as param. The other settings we have to do for the inertia relief that I will show. So I will go to analysis, control cards, and click on title. So we'll go to next. And enter the title name as inertia relief. Then I'll go to next again, previous, and select the param card and check the box in front of INREL, that is inertia relief, and under inertia relief volume 1 I will select -1 as the value. This requires that an inertia relief analysis has to be performed. So then I will click on return. Again I will click on return. Then I will save this file. Click on save. Go to analysis, radios, export option to all, run option to analysis, memory option to default, and click on radios. So once I click on radios, a solver window will come. So my analysis, then I will split the windows into two. Go to open folder, select the inertia relief std file and say apply. Or I can go to HyperWorks result file. Go to contour and say apply. So this is the value of deformation, and stresses are this much are the stresses due to the forces. Now we will see the animation by changing the deformed value. So in this way we have ended with 3D inertia relief. Now I will move to the next tutorial, that is 3D buckling analysis using radios. In this tutorial we will learn the steps required to perform the buckling analysis using radios. This tutorial will use the following exercise to set up the structural model for buckling analysis, that is creating boundary conditions for buckling analysis and post-processing the results. So we'll see how we can perform that. So I will open that file and we will see the analysis on performing the buckling analysis. So for the buckling analysis, first my material properties and components are created. As you can see, I will cross check it whether it is properly assigned or not. So I will change the color of it and also the material color. So you can see on the elements, if I am changing it by component, by property, by material, it is also getting changed. Fine. So we'll create the load collectors. We'll start with defining the load collectors. For the buckling analysis, I will first create the load collector as SPC. Give him a defined color and say create. Then we'll create another load collector as buckling loads. Defining a color, say create. So you can see my two load collectors I have created. But for the buckling load, I have to define a card image too. So I will create on the card image and provide the value of EIGRL as a card image and click on create edit. So I will go to create edit panel, enter the value of V1 as 0 and ND stands for 2, that is number of modes. So this tells radios that you would like to extract the first two buckling modes. So I will then click on return. Again I will click on return. So I will make the SPC1 as current and apply the constraints on my model. So analysis constraint. Select the bottom nodes, so I will select any one and click on nodes by face, or another option is I will make it in this way, so I can select all the bottom nodes and deselect all the rotational degrees of freedom and click on create. Now I will go to return, analysis, forces, and I will create one more load collector as static loads with no card image. Say create, changing this color. So analysis, forces, again making in this XY plane, selecting these nodes, applying the force in Z axis of minus 10,000 per node. And say create. Then the last step is to define the load step. So I will go to analysis, load step. I will select the type as linear. First I will enter the name as linear, then select the type as linear static. Check the box in front of SPC and select SPC. Check the box in front of load and select static load and say create. Then I will enter buckling. Select the type as linear buckling. Check the box in SPC and select SPC. Select method structure as buckling load and stat subcase, that is static subcase, as linear. That static stat sub, that is static subcase card allows for the selection of linear static subcase for buckling analysis. Then I will click on create. So my load step is created, and then we will save the file and run both the analysis simultaneously using radios, that is buckling and linear both. So I will split the window into two, browse the folder and say apply. So this is the linear one, and if I change this one is the buckling. So buckling modes, this is first, second, these are the two modes. If I put it in the animation, if I increase the deformation, say for example 10, so you can see this is due to the first mode, this is second. Animation due to first and second. If I make it in wireframe so you can view it more properly. So in this way we have ended with the buckling analysis. So I will pause this, click new. Here also I will click on new and transform it into 1. Now we'll move to the next tutorial, that is connection of dissimilar meshes using C-weld element. So in this tutorial, an existing finite element model for a simple cantilever beam will be used to demonstrate how to connect dissimilar mesh using C-weld element. So this exercise includes setting up the problem in HyperMesh, submitting the job, comparing results with control example. So I'll open the file. These are the dissimilar meshes which are not connected. So we'll make them connect using C-weld element and then see the results. So on the model browser you can see my load collectors, components, materials, properties, everything is defined, predefined. So in this tutorial I will see how to create C-weld elements and how to make it in analysis. क्या त्रास है भाई तेरे को, क्या त्रास है तेरे को? So in this tutorial we will see how to create membrane elements for this type of dissimilar meshing, how to connect them. So this file contains two components, that is solid fine and solid coarse, as you can see. These unconnected components are to be connected by C-weld element using the grid to element option. In order to achieve this, membrane element need to be created on the matching phase of solid coarse and solid fine components. So we'll first create property for it. So I will go to property collector icon. Enter the property name as membrane coarse. Define a color. Select type as 2D. Card image as special. And material as steel. User as blank, and in this again I will select user as blank. Setting the thickness of it as 1 e to the power minus 6. Then I will click return. Again I will click return. So my property as membrane coarse has been created. Similarly, I will create one more as membrane fine. Type as 2D, element P shell, material as steel, created it. Check the box, make it blank, make it blank. Enter the thickness value as 1 e to the power minus 6. Say return. I will define a different color for it. And click return. Then I will create a component as membrane coarse with a property of membrane coarse. Then I will just recheck it that I have selected the proper property or not. Yes, I have. Then I will just check the box of course of these two, and we'll go to tools. faces, select this and click on find faces. So these are the member elements I have created on the faces, as you can see. Then I will off these and keeping only the face one as the current or the only one. Then again I will go to tools, organize, select the elements by face and destination to membrane course and click on move. And delete these faces. Now I don't want them. So you can see I have created a membrane elements here. Again I will create one more component as membrane find. Select the property as membrane find and click on create. Similarly, I will create the faces for it. So I will go to tools, faces, select the component, click on the face, go to tools, organize, element by face and click on move. Then delete this. So now I have two components, member find and member course. So you can see this. I will change the color so it will be more visible, as you can see. Now I will create the weld elements. So I will go to properties, enter the property name as weld, click the type as 1D, card image as P-weld, material as steel, click on create edit, enter the D value as 0.1. Then I will click return. Again I will click on return. Then I will go to components and create a component for weld, defining the properties and say create. Then I will go to 1D, spot weld. We will select using elements. We will click on elements and say displayed. And in weld we will select the rod, select the properties as weld, search tolerance, we will enter the value of 0.1, click on the nodes by collector, select the member find You click select, then we will click on create. Once I will click on create, it will create the weld elements. If I click return, you can see it has created. If I off this, it has created the weld elements, the connecting weld elements. Now I will save this file. So in this way you can perform the analysis using weld element for dissimilar meshing also. So now as you can see, my analysis has got completed. So I will split this window into two. Go to folder option, select the file, say apply. I'll make it bigger. Go to deformation and say apply. If I go to animation, you can see because of the connection, the analysis is possible and it is happening. If there is no connection, so the analysis will not perform. So I can off this weld elements. So now it is of no use. And if I on this meshing, so you can see even the meshing is not connected, still the analysis can be performed by connecting those using weld elements. So in this way, we have ended with this tutorial. So I will pause this, click on new. For this one also we will click on new. And then we'll move to the next, that is analysis of composite aircraft structure using PCOM-G card. In this tutorial, we'll take you through the process of developing a ply layup definition for a composite structure using PCOM-G card and shows the advantages of post-processing the result with global plan numbers. The traditional definition method using PCOM-P is introduced first here to ultimately show the practical advantages of using PCOM-G for the given scenario. Since the structure, loads and boundary condition are symmetric about the x-axis, only one half of the structure is modeled with the suitable boundary condition and applied to enforce half symmetry. In this exercise, you will see how to retrieve the HyperMesh database file, retrieve the model setup, submit the job, view the results, set up the problem in HyperMesh by redefining the laminate properties with the PCOM-G card, and again submit the job, view the results. So we will open this file. Frame.hm. And directly we will submit the job. As on the model browser you can see everything is defined, so we will directly submit the job. First run, I will name it as first run. So my analysis is completed. I will split the window into two. and browse the file and view the results, that is displacement, and composite stresses, layer number say 3, averaging method to simple or say none, and say apply. So the stresses value does not vary gradually in top face region, as you can see, but suddenly decreases to a lower value across the flange to rib skin component, looking at the table of the laminate property of flange 1. So now we will see how to redefine and using the PCOM-G card, defining the property and getting a proper results. So I will make this in this way. From the 2D page, I will go to HyperLaminate. This will redirect us to a new GUI of HyperLaminate to define the composites. So this is my HyperLaminate GUI, where you can see the different configurations for different components. So we'll update the PCOM-G card and right click on it and select new and rename it as skin inner Then I will go to add update plies and under GPLY I will enter value as 1. Select material as carbon fiber. Thickness I will enter as 1.2. Orientation as 45 degree. S out as yes. And click on add new ply. We'll proceed the same for second. Material as matrix. Thickness 0.2. Orientation 90 degree. S out yes. Add new ply. Similarly 3. Again carbon fiber with a thickness of 1.2, but the orientation is -45. S out yes. Add new ply. Fourth, matrix 0.2 minus 90 degree, S out yes. Then the last one is carbon fiber 1.2 orientation 90 degree, S out yes, add new ply. So I have defined these many different plies, and then I will click on update laminate. So this will update my laminate. Then I will create one more pcom G with the name as rip underscore GPLY. GPLY ID as 11, material carbon fiber, so ID as 11, material carbon fiber, thickness 1.2, orientation 0, C out yes, click on add new ply, 12th matrix 0.2, orientation to 45, S out yes, add new ply, 13 matrix 0.2 minus 45 degree, add new ply, 14 carbon fiber 1.2 45 degree, add new ply. Then I will click on this and create a duplicate of it, and rename it as flange rib skin GPLY. In this we will add two more as 13 matrix 0.2 orientation minus 45, S out yes, add new ply, 14 carbon fiber 1.2 45, add new ply. And click on update laminate. So I will cross check it whether all are updated or not. So yes, all are now properly updated. Then I will click on file and say exit. Yes. Then I will click on file, import solver deck, FE overwrite, So by this, it overwrites the file, the earlier pcomp file with the pcomg. So I'll go to 2D hyperlaminate and check the properties. So you can see all the properties are now assigned to it. So again I will close this and again submit the model. So file, save as model. Save. Analysis. So from the analysis page, click on radios, export option to all, run option to analysis, memory option to default, and solve this file. Split it into 3 so that we can view all the 3 results simultaneously. Now we will import the third one, the second result, H3D file, contour, composite stresses, P1 major stresses for the third apply. So in this way you can see they are more different than the earlier one. So in this way I have ended with this training session, day 5 analysis part 1. Thank you very much for attending this training session. If you have any queries or any suggestions to improve this training series, feel free to drop us a mail at edu-support@india.altair.com.